Okay, number 9. We have this block. Now, look, they tell us the mass is 4 kilograms. This 4 kilograms here, is this gonna become part of the solution? No. Do electric fields care about mass? Not at all. The only way that mass would matter would be if gravity could somehow act on it. You know, like this situation here. You know, if there's some sort of vertical change in the position of the object. So, very common in physics to have too much info. The mass of the object's not going to factor in. Okay, however, we're told that there's a charge. Okay, the charge of this guy is 50 microcoulombs, which is 5 times 10 to the negative 5 coulombs. And the spring constant here is 100 newtons per coulomb. What else? It's on a frictionless surface. That's important. No friction. The system is immersed in a uniform, uniform electric field. The place that you find a uniform electric field is between oppositely charged parallel plates. This is where you'll have a uniform electric field, right? In between oppositely charged parallel plates. So you can just kind of visualize, you know, if you want to really wrap your brain around this problem, you can kind of visualize that over here is a positive plate. Over here is a negative plate, and then there's an electric field in between, like that. Okay? But for now, I'm going to move this. Okay, this electric field is 5 times 10 to the 5th volts per meter. That's 500,000 volts per meter. Okay, the first question is, if the block is released at rest when the spring is unstretched, by what maximum amount does the spring expand? Okay, so this block carries a charge. It's a positive charge. So can the electric field act upon the block? Yeah, because what do electric fields do? They exert force on anything with charge. And does everybody see why gravity is not going to factor in here? Because which way is gravity acting? Gravity's acting that way. Can gravity get in there and affect the motion? Nope. That's why the mass doesn't matter. So ignore that mass. Okay, so what we're looking for is this. So the block starts right here. It's released from rest, and the spring is going to go doing. It's going to stretch some displacement, delta x, and the block is going to come to rest over here. So for a split second, the velocity is going to be 0 meters per second. And then what's going to happen? What would happen after the block goes pulls the spring, it goes doing? Is the block just going to stay there? No. What would happen? It's going to bounce back. So notice over here on the right, I have this situation set up because, look, I always like to relate this to gravity, because what happens in a gravitational field is remarkably similar to what happens in an electric field. So here we have a situation where the work is being done by an electric field. Here we have a situation where the work is being done by a gravitational field. So let's look at the gravitational field situation just real quickly. Here's the identical situation, but with the gravitational field. Because if you can do the gravitational field, you can do the electric field. So look, this object starts at rest, okay? So initial velocity here is 0. And then this guy has some mass m. So you release him, and then it goes like this. The spring is going to go doing down like this, and then what happens for a split second? Velocity goes to 0, and then what's going to happen to that mass? It'll bounce back up again. So in this situation here, how could you find this delta x? Well, what type of energy does the block start with up here? Potential of gravity. No spring yet, because the spring is not stretched, right? You're starting with potential of gravity. Then the spring goes stretchity, 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 stretch. What type of energy do we have down here? Potential of spring, right? Assuming no friction, what will be true about these energies? They'll be equal. So look, potential energy is mgh. Actually, in this case, not h, mg delta x, because that is the h, mg delta x. And then who remembers equation for spring? Energy of a spring. Nice. 1/2 kx squared. So you set those equal to each other. You go mgx equals 1/2 kx squared. One of the x's will cancel. So then x is going to be 2mg over k. Now, dudes, let me just make a prediction here. The answer for over here, this delta x right here, it's going to be, so look, I'm just going to make a prediction. I'm going to show you how awesome physics is. This x is going to be 2. Now, instead of m, it's going to be what? Q. Instead of g, it's going to be e, and then k. It's going to be 2qe over k. Just change the m to q, change the g to e. It's the exact same thing, dude. You guys see what I'm saying? All right, now let's solve it with the electric field, okay? Let's revert this. Okay, so let's solve this now. So this thing's going to start here. This guy's a positive charge. He's in the electric field. We know this electric field. 500,000 volts per meter. Q is 5 times 10 to the negative 5 coulombs. K is 100. Okay, so this thing's going to go doing some distance x, okay? And then it's going to stop for a split second. All right, what type of energy do we start with over here? Potential energy of the electric field. No, it's not spring yet. Instead of it's not a gravitational, it's an electric potential energy. Electric potential energy. Okay, then the block goes like this. It goes doing, stretches over here. What type of energy do we have over here? Potential of spring, right? Assuming no friction in between, which they say right here, frictionless. Assuming no friction in between, what will be true? Potential energy electric is going to equal potential energy of spring. Now, how do we get potential energy electric? Check it out. I need some room. Let's erase this. So 2 equations that you should be familiar with. Potential difference is change of potential energy per charge. And then potential difference, if it's a uniform electric field, which we have, if it's a uniform electric field, then we can also go E times X, where X is the distance. Now, substitute these guys together. Substitute them together, you're going to get EX, right? Just take this and plug it in up there, equals change of potential energy, and that's an electric potential energy. Electric over charge. So then the change of potential energy is going to be QEX. Guys, I want to show you something. Let's look at the gravitational equivalent just real quick. What's the gravitational equivalent? Q becomes what? M. E becomes G. X would be H. It's the same thing. You know, QEX is MGH, but it's just for, you know what I'm saying? Okay, so basically this potential energy right here is going to be QEX, potential of spring, 1/2 kx squared. One of the x's cancels, so x is going to be 2QE over k. Did I predict it or what? I predicted it. So you plug the numbers in. I'm going to let you do the algebra. When you plug the numbers in, you get 0.5 meters. That's the answer to A. Okay? Now, B. Second question. What is the equilibrium position of the block? Okay, I want to review what is equilibrium? Equilibrium is a fancy name for not accelerating. If you're in equilibrium, you're not accelerating. So let's look at the gravity one again real quick. Look at this mass is going like this. It's going doing down to here. It's going doing, 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 doing. Where would the equilibrium be? Directly in the middle. When the block is right here, when it's right in the middle, this is where the acceleration is 0. Right in the middle, acceleration is 0. What's the acceleration there and there? It's a maximum. right? Because look, when it's down here, when the block is down here, which force is bigger? Rude. So look, when it's at the bottom, guys, when the mass here is at the bottom, there's a down force and an up force. Which force is bigger? The up force. Because what's going to happen? It's going to shoot up, right? When the block is at the top, when the block is up here at the top, the only force is down, so it has to be accelerating. Only when it's in the middle, for a split second, the down force and the up force of the spring, for a split second, these two forces cancel. They're equal, right? That's where acceleration is 0, in the middle. Okay, so same thing here. So this guy starts here. He ends over here. He goes doing, right? The acceleration here is a maximum. The acceleration here is a maximum. Right in the middle, what's the acceleration? 0. So if you look at the if you look at this object when it's at the middle, right here, right there. So remember, the electric field's going that way. Okay, so what are the forces here? We have force of the electric field to the right, and then we have force of spring to the left. All right, what's the equation for force of spring? Kx. What's the equation for force of electric field? QE, not mg, but QE. So these two forces are canceling at the equilibrium. That's what equilibrium means. Kx equals QE. So x is going to be what? Kx, no, x is going to be, come on, Spaldo, QE over K. So you plug the numbers into that, and you're going to get 0.25, which happens to be half. So what was our first answer? The first answer was 0.5. So notice that this answer is directly in the middle. Ba-bam. You might want to watch this video at home. Watch it again. Show your friends.